Class, good morning. So we come now to the third chapter of the topics on thermodynamics 2. Okay, so let us now come to the power cycles. Okay, so by this time, so I will show to you the flow of the Rankine or the basic Rankine cycle and the basic diagram. So in this topic class, so we'll notice that the simple Rankine cycle is like this. So of course it is composed of the boiler. We have here the turbine, the condenser, and then the pump. Okay, so what's the purpose of this boiler? So basically the boiler develops a steam. Okay, so converts water into steam, and then the steam will proceed to the turbine. So basically, it drives the steam turbine, and then it produces power. So after the steam was expanded, of course, in the turbine, it will go to the condenser to change the steam into water again, and then it will be again fed to the boilers to complete the cycle. Okay, so here is class the basic diagram. Okay, so the processes now, class of the Rankine cycle is like this. So 1 to 2 is isentropic expansion in the turbine. So that's why S here is equals to constant. So 2 to 3, constant pressure, rejection of heat in the condenser. Okay? So during the change in phase of the steam to water, there is a great amount of heat that is removed. Okay? So another is 3 to 4, so adiabatic pumping. So again, the process is isentropic. And then 4 to 1, the constant pressure heat addition and the boiler. So take note class that the Rankine cycle is composed of two isentropics and two constant pressure processes. Okay? So take note class, two isentropics and two constant pressures. Okay? So we have here class, in an ideal cycle, the state of steam leaving the boiler and entering the turbine are the same as well as the state of feedwater leaving the pump and entering the boiler. So this means that there is no pressure drop, of course. Okay, so the assumption. So this is class ideal. Okay, there is no pressure drop and no heat leakages in steam line and feedwater line. Okay, so this is the assumption. So the quantity, so the quantity of the working substance with the system is constant. So this implies that there is no leakages in the system. Okay. So here is now class the analysis of the system. So we will discuss class one by one. Okay. So first we are going to isolate the boiler. Okay. So we are going to detach the boiler, of course, to this from the system. So the heat added class and the boiler. Of course, the heat added is also a function of the heating value of the fuel and the, of course, mass of the fuel feed to the boiler or to the furnace rather. Okay? So the analysis class here is energy entering is equals to energy leaving, or energy in is equals to energy out. Okay, so take note class of the arrow. Okay? Of the arrow where the cycle flows. Okay? So the entering class, of course, is the heat added. So as what I have said, this heat added is a function of the mass of fuel and the heating value of the fuel. Plus, okay, entering class is the enthalpy at 4. Okay? Or enthalpy of the feed water. Okay? That is class equals to the enthalpy of the leaving steam from the boiler. Okay? So 1 at 1. It sub 1. So, in order to determine the heat added, of course, we are only going to change or determine the change in enthalpy or the difference between the enthalpy at point 1 and the enthalpy at point 4. Okay? So, that is class the heat added. Okay? So, I think it is very clear. Okay? Next, another class is the heat rejected in the condenser rather. Okay? Condenser. Heat rejected. Again, class, the process or the analysis is only energy in equals to energy out always. Okay? So, the the assumption, of course, is all or are all constant pressure. Okay? So, if we isolate one system, of course, in the entire, okay, say for example, the boiler, the condenser, isolate from the system, we treat that as constant pressure class. That's why we are going to assume that energy entering is equals to energy leaving. Okay? So, again, energy entering is the enthalpy at 2 and energy leaving is equals to the heat rejected plus the enthalpy at 3. Okay? Getting now the heat rejected class, that is equals to the difference between the enthalpy at point 2 and enthalpy at point 3. So take note class that the enthalpy here at point 2 is equals to the enthalpy of the leaving steam in the turbine. Okay, how you are going to determine that class? Take note that the process inside the turbine is isentropic. So that is why H sub 2 is equals to HF at 2 plus X multiplied by HFG, where the X class, of course, is the quality of steam leaving the turbine. And H sub FG is the enthalpy of the mixture at back pressure or at condenser pressure. Take note class, back pressure or condenser pressure are the same. Okay? So, and at 3, the enthalpy at point 3 is equals to the enthalpy of liquid at back pressure. Take note class, enthalpy of the liquid at back pressure. Okay? So, what is complicated here class, if you do not know, if you are the beginner, is determining H sub 2. But it is very easy. So, take note that S1 or the entropy at 1 is equals to entropy at 2. Okay? Entropy at 2. So, getting now the values of the entropy. So, entropy at 2 is equals to entropy at liquid at 2 plus X entropy of the mixture at 2. And then, getting now the value of X, you will obtain the quality of the steam and then substitute it to H sub 2 equals to H sub F plus X H sub FG. So, I think class, it is very clear. Okay? Next. So, another we have here in the turbine. Okay? So, isolating again the turbine. So, once we isolate this turbine, the process that we are going to, or the consideration that we are going to use is constant pressure. But if it is all connected, of course, the process inside the turbine is isentropic. Okay? So, again, class, energy in is equals to energy out. So, what is in its entering is the enthalpy at 1. So, where will you find class the enthalpy at 1? Of course, the enthalpy at 1 is obtained from table 3. So, if the temperature and pressure of the steam entering the turbine are given, then proceed to table 3 or by 4. Okay, so you can easily determine the enthalpy at 1. Okay, and then look for the entropy also at 1 is 1. Look for is 1 automatically. Okay, so in preparation for the calculation of H2. Okay, so and then of course leaving of course is the work, and then enthalpy at 2. So again class, I already mentioned how you are going to calculate the enthalpy at point 2. Again, so I'll repeat. Okay, so after getting is sub 1, that is equals to is sub 2. And then after getting is sub 2, equate it with is f2 plus x is fg at 2. And then get the value of x. And then substitute h sub 2 is equals to x f2 plus x, where that x is the obtained value of x from the entropy. Okay? And then multiply it by hfg at 2. Okay? So, very clear class. Okay? So, next. So, if class, the kinetic energy is considered. So, sometimes, we considered always the kinetic energy because of the velocity and the mass of the steam entering the turbine. Okay? So, if it is included class, again, energy entering is equals to energy leaving. So, you consider or you include the kinetic energy at 1 and kinetic energy at 2. So, it is class obvious if it is needed because the velocity is always given if the kinetic energy is included. But if there is no velocity given, you see to it that it is not included in the calculation. Okay? So, getting now class, the work if the kinetic energy is given, so that is the difference between the enthalpy at 1 and 2 plus the kinetic energy, 1 half mv square. Okay? 1 half mv square. So, this G class is not the, so this is a constant. Okay? So, the constant of proportionality, this is not the gravitational acceleration. Okay? So, take note of that class. Okay? So, but if it is in English, so it becomes G. Okay? So, take note of this G class. So, this is constant of proportionality, not gravitational acceleration. Okay? So, another, we have here the pump work. Okay? So, take note that the pump, if it is equipped, of course, in the system, the process inside the pump is isentropic. But if it is, of course, detached or isolated from the system, the process is, again, constant pressure. Okay? Energy entering equals to energy leaving. So, what is H sub 3? Okay? So, H sub 3, of course, obtained from the enthalpy of the liquid at back pressure or at condenser pressure. And W sub P is the work in order for a pump to operate. And then equals to the enthalpy at 4. Of course, enthalpy of 4, at 4 rather, is equals to the enthalpy of the liquid equal to the boiler pressure. Okay? Equal to the boiler pressure. Okay? So, unless otherwise specified. Okay? So, getting now the pump work equals to the difference between H sub 4 and H sub 3 class. Okay? So, approximate pump work class. Okay? So, we have here the assumption. So, this is an approximate pump work. Water is incompressible. So, therefore, the specific volume at 3 is the same as with the specific volume at 4. Okay? So, another assumption is that change in internal energy is negligible. So, that's why U sub 3 or the internal energy at 3 equals to internal energy at 4. Okay? So, again, energy balance, the pump work now is equals to the pressure, of course, at the boiler multiplied by the specific volume minus the condenser pressure multiplied by the specific volume. And since there is no change in specific volume, we have to replace B4 by B3. Okay? Or simply B3 by P4. Okay? So, or simply pump work equals to the specific volume multiplied by the change in pressure between the condenser and the boiler. Okay? So, take note class. So, we have here the net cycle work. Okay? So, net cycle work, of course, is the work of the turbine minus the pump work. Okay? And the net work is equals to, of course, H sub 1 minus H sub 2 minus W sub P. Or simply, for thermal efficiency, E sub E class, okay, thermal efficiency E sub E. That is equals to the work net over the heat added. Or simply, H sub 1 minus H sub 2 minus the pump work, or H sub 1 minus H sub 3 minus the pump work. Okay? So, of course, you can multiply it class by 100%. So, that is for thermal efficiency. Okay? So, another is steam rate, M. Okay? So, take note class. So, steam rate. So, what is this? So, it is a mass flow of steam required to produce unit power. Okay? So, a lower value of steam rate means that the smaller amount of steam is needed to develop the desired power output. Okay? So, again, class, let P is equals to the power output, and let W is the work done, and M is the steam rate in kilogram per kilowatt hour. Okay, so steam rate class, from the basic definition, mass flow rate, divide power output. So substituting the unit class in order to be simply analyzed. Okay, so mass flow rate is in terms of kilogram per hour. So power output is equals to the kilogram per hour multiplied by the change in enthalpy in kilojoules per kilogram. So, since kilowatt class is included here in the unit, so we are going to change 1 hour equivalent to 3,600 seconds to make it kilowatt here in the denominator. So, hour will be cancelled out, kilogram will be cancelled out, kilojoules per second is now kilowatt. Okay, so that is quite class. So, rearranging the equation, so we are going to put 3,600 seconds at the numerator. Okay, so divided by the work. Okay, so my mass flow rate class will be cancelled out. Okay, since this is also mass flow rate. Okay, mass flow rate multiplied by work. So that is why class, the equation will become, for steam rate, automatically 3,600 divided by the work. Okay, divided by the work. So the unit now is in terms of kilogram per kilowatt hour. Okay, so it is clear class. Okay, thank you very much class. So that's all about my presentation today. Thank you.